Thank you. Okay, thank you everyone. As you see, I'm not one of the authors, and I'm the proxy author for this paper, the CMCLRec, the cross-modal constructive learning for user code start sequential recommendation. And this paper is from Nanjing University of Information Science and Technology. So here is a continent. So firstly, it's in today's fast evolving internet era. So people just often face an overwhelming amount of information beyond what they need or they can handle. So since the information reductivity and overload are prevalent, the recommender system were developed to address these challenges. Actually, the long tail effect in recommender system highlights the significant demand for both popular and niche needs with many resources underutilized. Right? So actually, recommender system use those to enhance fairness by covering less popular niches. And besides, the recommender system do not only address enhancing click-through and conversation rates, but also provide personalized services tolerant content recommendation to individual users' preference and behaviors. And this dual capacity do not only improve user engagement and satisfaction, but also optimizing the content delivery based on user interactions. Okay. And so this paper mainly about the traditional systems, such as those based on continent and collaborative filtering information models. The interaction between the users and the items statically can only capture users' general preference. Okay. So, but because the modeling is static and the traditional recommender system are unable to accurately predict users' dynamic preference and cannot offer real-time recommendations. But actually, sequential recommender system model, the interaction between the users and the items are dynamic sequences and utilize the dependency within those sequences to capture current and recent user preferences and providing more accurate recommendations. However, due to the heavy reliance of the sequential recommender system on users' historical behavior sequences, and their effectiveness significantly decreases for the new users or the newly added items, which is known as the cold start problems. And since the sequential recommendation models are almost entirely depend on the behavior sequences for making recommendations, and they often find themselves at a loss when dealing with cold start users. So existing solutions to the cold start problem actually face three main challenges. So firstly, existing cold start models often differ significantly from the advanced sequential recommender models in terms of model structures, feature representations, and parameter settings, and making them difficult to integrate. Besides, training cold start models typically requires specifically datasets that necessarily additional manual labeling or just increasing significant labor and time costs. And finally, since cold start models need to make recommendations based on the various sparse features of new users, they actually require high inference capabilities, resulting in a high training and inference cost. Okay, so to address this problem, this study actually proposed a solution that involves the use of deep learning techniques to generate simulated behavior sequences based on the warm user feature informations. Okay, so since those simulated sequences can be directly used as inputs for sequential recommendations models for cold start users, this framework is theoretically compatible with any embedding-based sequential recommendation models. However, the proposed solution also faces three key challenges. So first, a considerable amount of users' registration data is complete. Right? So actually the feature continent is not rich enough, make it very difficult to infer the behavior sequences. And in addition, the user feature information and the user behavior sequences are not of the same data type, resulting in a significant distributional discrepancy, and finding mapping using conversational networks is challenging and often fails to converge. And lastly, directly incorporating a cold start module into conventional sequential recommendation model would significantly increase the number of model parameters and will lead to very difficulties in training or even failure to converge. Okay, so this model is the overall framework. So this module all proposed in static consistency 3 main components: the data augmentation module, or cross-modal constructive learning module, and a sequential recommendation module, as illustrated in the figure. Okay, so next we will introduce them one by one. So firstly is the data augmentation model. So due to the incomplete user information and the features, and the data augmentation model actually adapts constructive learning approaches to enhance the feature repetition of the data. So actually, it motivates the model to minimize as in the figure, to the distance between the embedding with the similar users in the embedding space, while maximizing the separation between embeddings related to different users. And for the warm user data, the user feature actually undergoes 2 different masking operations that optical parts of the features. So subsequently, the 2 encoders share the same parameters, encode the results of the both masks, and aiming to minimizing the constructive loss between the encoded output, and the same operation is also applied to the user's behavior sequences. And this model is employed self-supervised learning approaches. Okay, so finally, the encoder uses those unmasked original user features and behavior sequences for data augmentation and making them valuable for the next module. So actually, the traditional neural network struggle to efficiently process the entire sequential informations, and they have very difficulties in extracting the implicit combination of these features. So therefore, in this cross-module constructive learning module, self-attention is utilized for embedding construction and utilizing attention decoder to encode the enhanced informations. And then the encoder is employed to encode and reconstruct the attention encoded data, and striving to retain as much as possible the original features as possible. And this instructs compressed encoding and minimizing the distribution gap between the user features and the compressed encoding of the behavior sequences, and guiding the converge of the cross-module mapping. And this module also employs the self-supervised learning for training, and reducing the data requirements and alleviating the overall training burden of the model. And finally is a preliminary model is enhance the behavior sequences for ACT users and generate simulated behavior sequences for cold start users. And therefore, they can theoretically allow the capability with any embedding-based sequential models. And here in our study, we test the SIGIR models. And for the active users or the warm-up users, attention encoded behavior sequences are directly used as an input for the and the next recommendation model. So for the cold start users, the encoder for the user features along with the decoder and for behavior sequences is employed to generate simulated behavior sequences and used for the input for the subsequent recommendation model. Okay, so here is the experimental result, and here we utilize 2 datasets. One is CMCLRec, and another is Xiang. So the experiment and both datasets, the 30% of the users are allocated to the test set, and 50% are left unadjusted, while remaining 50% have their user item interaction removed to simulate as the cold start users for each dataset. And the rest of the users are divided into training dataset and the valid dataset at a ratio of 8.4 and 8 and 2. Okay, so here is the overall performance, and the data from the table clearly show that overall recommendation, the cold start problem, cold start recommendation scenarios, and active user recommendation scenarios, the model, our method can also outperform the best baselines, and is actually attributed to the successful establishment of the mapping between the user features and through the cross-modal constructive learning. Is effectively improving the feature distribution of the cold start problem, cold start users. And furthermore, the ablation study also further validated that the effectiveness of the three modules. Okay, so finally, it is the figures, the T3, and it's visualizing the research showing the distribution gap between the simulated user behaviors and the cold start users and the behavior from the active users. So the cold start users are marked as blue and the warm-up users are marked as red. So after supervised learning, it's evident that our model effectively reduced the distribution gap between the cold start and active users, and confirming that the relation behind using simulated behavior sequences to recommend for cold start users. And the figure also reveals that our model can generate different simulated behavior sequences for different cold start users, and confirming that those simulated sequences are not just default behavior sequences. And okay, so and thank you. So okay. Okay, so here is our conclusion. So our research has four main contributions. So firstly, the CMCLRec actually effectively addresses the cold start problem in recommender system by generating simulated behavior sequences. And this allows the model to provide a more meaningful recommendation, even for the new users lacking some interaction history. And besides, the model leverages the supervised learning, improving the quality of the recommendation without requiring additional label data. And in addition, the experiment revealed that our model can outperform the baselines and in three distinct scenarios: the overall recommendation, cold start recommendation, and active user recommendation. And finally, the effectiveness of the cross-module component is validated through the application study. So in the future work, we intend to extend the model capability to support additional recommendation algorithms, particularly those involving the graph network, such as GNNs. Okay. So thank you. So if you have any question, please mail to this email. So if you ask me, I don't know the problem, I don't know the answer. Okay. So thank you. Thank you.